Early life on Earth depended on a rare and scarce metal.
NASA-funded scientists have discovered something surprising about the origins of life on Earth. More than 3 billion years ago, the first living organisms were already using molybdenum, a metal that was extremely rare in the oceans and environment of that distant period.
This study, recently published in the journal Nature Communications, is the first to demonstrate that molybdenum was part of the biochemistry of life so early, challenging previous ideas about how primitive living beings managed to carry out reactions essential for survival. Today, molybdenum is common and essential for many biological processes. It acts at the center of enzymes that accelerate important reactions involving carbon, nitrogen, and sulfur. Without it, these reactions could still occur, but so slowly that they would not sustain life as we know it. Batul Kakkar, a professor at the University of Wisconsin-Madison and lead author of the research, explains that asking when life began to use molybdenum is the same as asking when fundamental metabolic strategies became possible. This metal is at the heart of vital biogeochemical cycles, such as the nitrogen cycle, which affect the entire planet. In the distant past, however, the scenario was quite different. Geological evidence indicates that molybdenum existed only in minimal quantities in ancient oceans. Its levels increased significantly only after the Great Oxidation Event, about 2.45 billion years ago, when microorganisms performing photosynthesis released large amounts of oxygen into the atmosphere. Before that, the oceans were poor in oxygen and certain metals. Because of this scarcity, some scientists imagined that primitive life might have first used tungsten, a similar metal that is still used today by organisms living in extreme environments. The idea was that life would have migrated to molybdenum only when it became more available.
However, new research shows that the story was not so simple. Using data on the presence of the metal over time and reconstructing the tree of life, researchers concluded that ancient microorganisms were already using both molybdenum and tungsten in the Archean period, between 3.7 and 3.1 billion years ago. This places the use of these metals well before the increase in atmospheric oxygen. Life didn't wait for abundance, it found ways to take advantage of what was available, even in limited quantities. One possible explanation lies in localized environments, such as hydrothermal vents on the ocean floor. These underwater winds release trace metals, including molybdenum, iron, zinc, and others, creating niches where microbes could access them. Even though the sea as a whole had little dissolved molybdenum, these hotspots provided enough for life to evolve mechanisms to capture and utilize it. Kakkar highlights that molybdenum was worth the evolutionary effort because it offers great catalytic flexibility. It works on a wide variety of substrates and redox conditions, making it especially versatile. This discovery has profound implications for astrobiology, the field that studies the possibility of life on other planets. Understanding how life on Earth adapted to a world very different from the current one with anoxic oceans and scarce metals helps scientists imagine how life could arise in worlds with distinct chemical compositions. It's not about looking for planets exactly like Earth today, but about mapping the evolutionary history of essential elements and considering different chemical inventories and oxygenation levels. The detection of extraterrestrial life needs to be metal-conscious, redox-conscious, and evolution-conscious, as the team summarizes.
The work reinforces an important lesson: life is resilient and creative. Even in the face of environmental limitations, early organisms found ways to use scarce resources efficiently. This broadens our understanding of habitable planets in the universe and reminds us that the biochemistry of life may be more diverse and adaptable than we imagined. Research like this, led by NASA consortia such as MUSE, Metal Utilization and Selection Across Eons, continues to reveal fascinating chapters in the history of life on Earth and opens new doors to the search for life beyond our planet. In short, molybdenum was not just a detail in ancient biochemistry, it was one of the key ingredients that allowed early life to thrive in a young and challenging world. Long before the oceans became rich in oxygen and metals, this research invites us to rethink what is necessary for life to arise and be sustained anywhere in the cosmos.